All right, so today I'm going to move on to talk about computing gravitational observables using amplitudes. So the two lectures in this one and the next one will be about two observables too. Yeah, two related but different observables. There's a basic idea that I'm just going to use throughout both lectures. Let me write what that is. Well, sort of either a basic idea or a three-step recipe. Okay, so the first thing I want to do is to pick an observable. So just some observable to talk about. Now, I want an observable which makes sense classically, and in QM. So in other words, classically and in quantum mechanics. Why? Well, it's because I want to talk about classical physics, but I want to talk about classical physics using the language of scattering amplitudes. And scattering amplitudes are things that we know about in quantum field theory. So I have to start out with a quantum mechanical formalism so that I can use double copy in amplitudes. And then I need to take the classical limit, right? So I want to have an observable that I can talk about in quantum mechanics, and then I want to take a limit and get a sensible observable in the classical case, right? So that's the first thing. Two. Okay, so the second thing to do, let me see, observable O, let me give it a name. The second thing I want to do is to pick a state in the quantum mechanical description. So pick a state psi. And I don't want to pick just any state. I want to pick a state that has a sensible interpretation in the classical theory. So in other words, I want to pick a state which happens to describe a situation that's in the domain of validity of the classical approximation, right? Now, there's a quantum field theory, that's the underlying thing, and then there's a classical approximation to the quantum field theory. So I want to pick a state that has a sensible classical description. So pick a state psi in classical approximation. Let me write it like this. In the domain of validity, of the classical approximation. Okay. And thirdly, well, the third thing is just the basic idea, really. The third thing is that the final state, right? So this is an initial state. So an initial state psi. So the final state, well, the final state is obtained from the initial state by acting with the time evolution operator over all times, which is the S matrix. Well, the final state is S psi. So for that reason, it's inevitable that the change in the observable is going to come out in terms of amplitudes. So delta observable okay, so that's a basic idea. And I'm going to go through these three steps now for one observable and after the break for another observable. Now let's see. Yeah, so I thought it might be no harm to give you some references to a little bit of literature here. So sometimes this story goes under the name of KMOC or KMOC, depending on how you think that should be pronounced. There's a review which I wrote on this topic, 2203.13025. Now, this is one prescription for getting classical physics from scattering amplitudes. There are other prescriptions. So this is the way I like. So there are other approaches. So there are some reviews about other approaches. So I'll just give you two more. references to read about. All very similar references, 13013, 013, and 2203.13024. They submitted one before us. Sometimes you win, sometimes you lose. Okay, now this isn't exhaustive. There's another approach which I wasn't able to find a review about, which involves using world line theories and methods of quantum mechanics. There are exponents of that method in the audience, Matthias, for example, and Jitze. So if you want to know about that, then you can bug them. Okay, just another way. All right, so the observable I'm going to talk about in this lecture is called the impulse. So this is step one. I have to pick an observable, right? So I'm going to talk about the impulse now. So this impulse, well, it's just a name for the total change in momentum of a particle during a scattering event. So AKA total change in momentum of a particle. All right, so excellent. So I am then going to define delta p mu of this impulse to be, well, I'll compute, first of all, the expectation value of the momentum operator. So big P mu is a momentum operator. So the expectation value of this momentum operator on a final state, right? So that's going to be P final. And I'm going to subtract from that the initial momentum. This is definitely lowbrow stuff. So you got the final momentum, you subtract the initial momentum, it's a change in momentum. The initial. So that's the impulse. It's a pretty straightforward thing. We can rewrite it in well, sort of helpful to rewrite it a little bit. So if I insert here S dagger S, which is unity, then I can rewrite the impulse like this: S dagger commutator of momentum operator. Right. So I chose to insert the S dagger S there. You could also insert it in the other place. Just some choice. You can play around with these things. You get fun expressions out of it. Anyway, yeah. So that's just a choice. Okay, now if I use S equals 1 plus IT, so S is 1 plus IT, well, obviously the commutator of P mu with 1 is 0, right? So there will be two terms. There's a term where I fish out the 1 from the S dagger. So then there will be a commutator of P mu with IT, and another term plus T dagger commutator of P mu with T. Okay, so that's the impulse. Now, more generally, if you have a different observable, well, just follow the same reasoning, but just shove in whatever that observable is. So let's say more generally delta O, it would be psi S dagger commutator of your quantum operator for O S psi. Okay, so and we'll see another example of it like that after the break. Okay, so that's the observable. Any questions about that so far? Awesome. I mean, either incredibly clear or you're tired because it's 4 o'clock on the 4th day. God, I can't count. Okay, very good. So that's the observable. Now let's go to step 2. I want to talk about the initial state. It'll take me a little while to talk about the initial state because I want to arrange it in the domain of validity of the classical approximation. So that'll take a little while to discuss. Okay. Now, first of all, I'm going to restrict to a situation where I have two different particles and I'm going to scatter them. So I'm going to restrict to scattering. Restricting to scattering is a bit of a minus, particularly when we want to talk about, say, LIGO physics. In LIGO, obviously, it's bound black hole systems. But there's a clue in, there's a clue about why I'm making this restriction. This is scattering amplitudes. So I'm going to talk about scattering scenarios. It will be nice to talk about bound state scenarios, and there are some methods to do that. They're not completely satisfactory. They work up to certain orders of perturbation theory. They're sort of good enough at the moment. But in future, it would be really great if I could start talking about bound states from the start, right? Now, it's a bit of a machinery to start talking about bound states and say it's not completely satisfactory. Anyway, so in these lectures, we're just going to scatter things. Okay, now, moreover, is that I want to scatter two different objects. This is literally supposed to be the picture of scattering billiard balls in classical mechanics, right? So the particles are different. I don't want to have a situation where I'm summing over identical particles in the final state or something. Not for my massive particles, at least. Okay, so in other words, take two different particles. So to make them as different as possible, I'm just going to make them be quanta of different fields. Right? So I'll make my particles out of quanta, and I'll take different fields with different masses. But I will assume that that my particles are stable. So the action will be something like, well, I guess there's gravity, right? So there's a root minus g, g mu. So I've got at least two kinds of particles because I want to scatter two different particles, g mu nu, d mu, so some scalar field I, some other scalar field I. I have some mass, phi I squared. Right. So they're just interaction gravitationally, right? Okay, good. Now, so thinking about the state which should be in the domain of validity of the classical approximation. Well, in the classical approximation, I'd be able to say that my two particles have well-defined positions and well-defined momenta, right? I could give these with exact precision. So classical exact positions Now, in quantum mechanics, obviously, we can't do that, right? There's the uncertainty principle, it's sort of an important thing. So I can't specify, give you a state which has particles with exact positions and exact momenta. What I can arrange is to have particles with positions that are reasonably well defined and momenta that are reasonably well defined, right? And if that uncertainty in the position and the momenta is small compared to other scales in my problem, then I can neglect it. Right? So that's the idea. I'm going to take the particles and put them in wave packets. And so they'll be plain wave states, but then put in wave packets such that they have positions, reasonably well defined, and momenta which are reasonably well defined. So in QM, in the quantum case, I can have negligible uncertainty. Okay, so the picture then will be something like this. So I'll have particles which are in wave packets, so they'll have some uncertainty in position. And so let's say that the wave packets have some spatial spread LW, which is supposed to be small. And they're going to be separated by some big distance, some big classical distance, which I'll call B. B is going to be the impact parameter. And so the impact parameter is the distance which you separate particles in a scattering experiment. So in other words, if I have particle momentum P1 and particle momentum P2, they're going to be separated through some transverse distance B, the impact parameter. So the idea then is going to be that LW is going to be very small compared to B, right? Excellent. Okay, so let's say the wave function spread then. Wave function spread will be, say, a distance LW in position space. Right. So notice, have in mind something like a Gaussian, right? So, a wave packet, a wave function looks like e to the minus x position minus some fiducial position squared over LW squared. Right. So that would be the Gaussian describing the position space wave packet. Well, then the wave function spread will be in momentum space. Momentum space will be h bar over LW. Right, so that just happens because of Fourier transformations. Is there a question? Okay, so the wave packet in Fourier space, in momentum space, will be some p minus, again, there might be some p star, and now the LW pops upstairs, and there's a h bar squared downstairs. I'm going to keep the h bars in all the formulae in this lecture. Well, I say that with a lot of confidence. I plan to keep the h bars in all the formulae in this lecture. If you spot any that's missing, yeah, you should let me know. All right. So negligible uncertainty then is going to mean negligible uncertainty. Well, very good. So I'll definitely want this LW to be very small compared to the impact parameter. Right, so the impact parameter says this transverse separation. Now, when the particles scatter, they don't always stay, a distance b apart. They will get closer. And they get, there will be a distance of closest approach. That distance of closest approach, we might call that LS. A scattering length. This isn't going to be super important, right? But there's just a distance of closest approach. Now, in perturbation theory, which I'm going to do, then this distance of closest approach is going to be roughly of order b, right? So I don't have to make a big difference between them. But in principle, indeed they get closer, but it's just that's a perturbation away from the b. So yeah, good. So that will be one requirement. But there's another requirement. And the other requirement is about the momentum space, uncertainty. So I will certainly want the mass of the particle to be well defined. I mean, the particle mass is clearly a meaningful thing classically. So I'll want the uncertainty in the wave packet to be small compared to the mass m. So that means that h bar over LW, is going to be very small compared to the mass of the particle. And I'll make another definition here. So I'll call m equal to h bar over LC. LC here is a Compton wavelength. It's technically the reduced Compton wavelength or something like that, but it doesn't matter, right? So it's just some measure of the Compton wavelength. Okay, so putting these things together, that means that the Compton wavelength is going to be very small compared to the size of the wave packet. And that in turn will be very small compared to this impact parameter, this LS. Maybe I'll just call it B. Okay, so this is a set of inequalities that we need to impose on our state. Okay. And that's more or less, that's it in terms of the requirements on the state. But there's another perspective on this, which is useful. So let me just spend a moment more on this. So another perspective. I suppose the thing about this this series of inequalities here is it's very intuitive, but it's all written in terms of position space. And we tend to compute in momentum space. So I actually want to figure out what this looks like in momentum space. And we can do that by the magic of inverting these. Now, let's see. So that means that 1 over LC is very much bigger than 1 over LW, and that is very much bigger than 1 over B. I'm remarkably bad at inequalities. So I'm doing this in a very step-by-step manner in the hope that I don't mess it up. Now I'm going to multiply it across by h bar. I told you I'm going to do it step by step. Okay, good. This one here was the definition of the mass. So the mass of the particle is very big compared to h bar over LW and compared to h bar over B. Now this quantity at the end is the interesting one. H bar over B, well, one way to think about what this thing is this thing is of order, so another definition, I guess, Q. Q here is the momenta of the particles that are mediating the interaction. So h bar over B might be useful for you to remember that the dimensions of h bar is mass times length. So when I divide by the B, I get a mass. It's a momentum. So this Q are the momenta of the mediators of the interaction between the particles. If you think about it in Fourier space, this might make more sense. This is the wave number, or 1 over B is the wave number of the Fourier modes of the interaction. Anyway, so these Qs are going to be the momenta of the particles mediating the interaction. And notice that Q then is very small compared to the mass m, and in particular compared to the momentum, right? The momentum is the mass times some velocity. So Q is small compared to P. And that's actually a very useful thing because I'm going to be working in momentum space. I'll encounter these Qs, I'll have Ps, and I'm going to expand. And anytime I see a small Q, I can dump it compared to a big P, right? It's also true from this inequality that Q is small compared to h bar over LW. And we will use both of these inequalities to simplify the expressions of the observables in the classical domain in a little while. Okay. Yeah, so there's a couple of remarks one could make about this before moving on. So I'm working here in, obviously I want to talk about classical physics, but I also want my particles to be point-like. So I'm going to imagine they're very small. The classical particles are small compared to other scales in the problem. So you can view these inequalities as being two inequalities, one for imposing the classical limit and one for imposing a point particle limit. So this one here is more to do with classical. Let's see. Classical. And here, point particle. Don't know why the hyphen. It's the point particle part. So I'm going to neglect any finite size effects. And classical objects can have various finite size effects. Simon already mentioned love numbers. That's a particular kind of finite size effect. I'll be neglecting that in these lectures. It's possible to include them, and that's very interesting. But the simplest thing to do is just have a completely structureless situation. Okay. Excellent. So, now to write the state, I need a little bit of notation. Okay, so I want to write the state in terms of wave packets. I'm going to work in momentum space, so I'll be writing an integral, all right, psi, as an integral over suitable momenta. So let me just integrating over dp1, dp2. I'll say more about what this measure really is in a moment. Right? So just think of it as an integral over suitable momenta. I'll put particle 1 in some wave packet, particle 2 in some other wave packet. In momentum, there'll be wave packets that impose this set of inequalities. By the way, I might fall into old habits. We used to call these the Goldilocks inequalities, where things were just right for the classical limit. Anyway, so these wave packets will impose those inequalities. I'm going to translate one of the particles with respect to the other. So I'll translate particle 1 through this impact parameter B. That's where it comes in. And then I will put two plane wave states of these different fields. So P1 is going to be a quantum of field phi1, and P2, quantum of field phi2, so it's different particles. Great. Now, so what do I mean by this integral here? Well, I'm integrating over states, on-shell states. So this integral will be over the phase space, the on-shell phase space of these states. So the measure, I'll write the measure as d phi. Well, I'll define a d phi of p. So this is going to be the integral over the on-shell phase space of a particle. So the definition will be, so an integral over 4 momenta, d4p, I'll say what these little hats are in a moment. A delta function with a plus setting the particle on shell. So here dp with the hat is just dp over 2 pi, just tidies up these 2 pi's. Don't really have to worry about the 2 pi's, but I have muscle memory for keeping them along, so I might as well. There is a delta plus of p, that is defined to be 2 pi delta of p, and finally, delta plus hat, delta plus of p squared just means delta of p squared theta of p0, right? So I'm integrating over on-shell momenta, delta p squared equals m squared, with a theta function setting the energy is positive, right? And then there are various hats that gobble up the 2 pi's. Okay. Very good. So the wave packet then, or the state. So we can write the psi as an integral d phi p1, p2, phi p1, p2, e to the I b dot p1 over h bar p1, p2. This phi here, this is just phi p1, phi p2. It wouldn't really be necessary to put them in different wave packets, anyhow. You could entangle them if you want. Okay, so that's our state. Yeah. Good. Any questions about that? Fantastic clarity. Excellent. Wonderful. All righty. So let's then move on. So now that's step 2. We've discussed the state in sufficient detail. So now let's go on to actually expanding the final state in terms of amplitudes, and we'll get an expression for the observable. So okay, so well, from over here, we have an expression for the delta p mu in terms of commutators.
Maybe this is a question, but phi1, p1, and phi2, p2, are they like Gaussians?
Yeah.
Okay.
Yeah, well, they're Gaussians. You should have in mind that they're Gaussians, but there is a little trickiness that this measure here has got, it's an on-shell measure. So if I integrate over the energy, the P0, to get rid of that delta function, the delta of P squared minus M squared, you'll get a 1/2 energy downstairs.
Yeah.
Right. So that's a little bit weird. If you think of ordinary quantum mechanics, we don't have that weird denominator. So big deal. So you just multiply the phi by a √2e. √2e by a 2e. Yeah, actually, it's probably better to make it a √2e. So you need to put something there that will handle these energy denominators. Actually, a square root is a better option. Then when you take expectation values of things, you get 2 √2e's, 1, 2. They cancel off, and now you've got a Gaussian. That's the simplest thing you could do.
Okay, thank you so much.
Yeah. Okay. Yeah. Good. Okay, so there is an expression for the impulse. Let me just write it down again. So I'm going to talk about the impulse on particle 1. So I should really talk about the momentum operator of particle 1. That's P1 mu T plus T dagger, P1 mu T psi. So the point here is this is the operator, the momentum mom op of particle 1. If you were to put the total momentum, the momentum of all of the fields in the problem, particle 1, particle 2, and the gravitational field, that will commute with T, right? The total momentum commutes with the S matrix. That guarantees conservation of momentum. A bit of a triviality in quantum field theory, but in the classical case, that's actually remarkably important. Classical dynamics often has some problems with conservation of momentum. Radiation reaction is the issue. You're guaranteed from the outset that radiation reaction will be incorporated correctly in this approach because you're doing quantum field theory, which is, satisfies conservation of momentum. So that's a nice aspect. Yeah, maybe I'll talk about that more tomorrow. It's kind of unlikely. I've got a long list of things I'd like to talk about tomorrow, and I only have 1 hour. So anyway, you can also ask me about it. A favorite topic of mine. Good. Okay. Now, so let's expand the state here. Do I have space? Yeah. So now, expanding this thing with this notation. So I have a phi. I have a psi and a bra and a ket. So they all have 2 momenta. So I'm going to have 4 on-shell momenta. There are questions.
Sorry,
just going back quickly here, why not the Fourier transforming P1
yeah. Yeah. Okay. So the question is, why have I just put a P1 here and not a P2, right? So I've translated particle 1 with respect to particle 2. So I could indeed translate particle 1 and 2 together, but all I really want is that one particle is separated from the other by some distance, b, and this just stops me writing e to the I b1.p1, e to the I b2.p2. It's a bit of a cheat. Actually, in many ways, it's nicer to keep it going on, but there's a finite amount of space on the blackboard. So I just set b2 to 0. I'm choosing I'm choosing to place particle 2 along the origin. Yeah, so it's a choice of coordinates. That's exactly right. Yeah.
Because you're integrating over P, I guess it's independent of the choice.
Yes. The physics won't care about this choice. I mean, ultimately, what the physics cares about is b1 minus b2 if you have an arbitrary origin, right? So I've set b2 to 0, and then b is the irrelevant quantity. Yeah.
Is b a 3 vector here, or is it a 4 vector?
No, B is a 4 vector. I have in mind that B is a 4 vector. Okay. But really, and it's maybe sort of indicated in this picture here, really there's only 2 components of B that are physical. There's some separation in the transverse plane. So for that reason, you can impose, it's a useful thing to do in many cases, you can impose a condition that B.P1 equals 0 and B.P2 equals 0. So that removes the 2 sort of irrelevant components.
Thank you.
Excellent.
Sorry. One quick question, just to make sure that things didn't go off the rails yet. I mean, when I'm thinking about these states, these are still like, can I think about them in terms of a Wigner classification of one particle states? Or,
yes.
So it's still the usual, quote unquote.
These are just, so I've hit the vacuum with a creation operator for field 1 to make the P1, and a creation operator from field 2 to make P2. Yeah, no funny business.
Okay, nice. Thanks.
Yeah, they're kind of trivial particles. Excellent. So here I am. So I'm expanding this expression for delta P, and I'm going to write out what the state is. So there's going to be 2 momenta in this psi and 2 more in this psi. So I'll call the final state, if you want, or this is an expectation value. So nothing is final state here. Well, I guess S psi is. I'm going to call the left thing P primes and the right P's. Okay, so now I'll have a wave packet from each side, phi star, P1 prime, P2 prime, phi, P1, P2. And there's this little translation operator, e to the I b dot p from each side. So e to the I b dot P1 minus P1 prime over h bar. Yes, and what's left, you see, I'm going to try to squeeze this in. There's P1 prime, P2 prime. So now I just expanding the actual, the field theoretic part of this thing times I commutator of P1 and T plus T dagger, commutator of P1 mu and T, P1, P2. Okay. Yeah. Okay. So this is one of the reasons why it's nice to have this notation for the phase space. It's nice to have a place to put all of these things that you're integrating over. You can get more and more of these, so you don't want to have too many. Okay. Yeah. Okay. So he wields the stick. Excellent. So now there's two terms here. There's a term which has a commutator. Well, I guess they're both commutated. There's a term which is 1t and a term which is 2. Right? There's a p mu t and then a t dagger p mu t. So the first term here is going to involve, the first term, so I'm just looking at the matrix element here, is going to involve p1 prime, p2 prime. So there is a factor of I. Well, let me write it like this. I guess the point here is that this momentum operator, it can act on particle p1 prime, and it will bring out a factor p1 prime. Actually, let me just write it like this. So there's the I p1 prime minus p1 mu, right? So this is this commutator. In one side, the p1 hits that p prime. It's the p prime there. In the other term, this commutator, the momentum operator is on the other side, and it hits the ket, and it brings out p1. Right? So you got this term here, and everything else is just p1, p2 prime, t. Right? So that's a 4-point amplitude. Right? So this is just a 4-point amplitude, p1, p2, goes to p1 prime, p2 prime. And then there is going to be the usual momentum conservation condition. Let me just abbreviate it like that. Now that's true to all orders, right? So this first term just always gives you a 4-point amplitude. In principle, it's a 4-point multi-loop amplitude. No restriction on the number of loops here. So good, this is coming out as promised in terms of scattering amplitudes. The second term is a little bit more complicated. So the second term here involves t dagger, p mu, and t. So now this second term, sometimes people give it a name. People call this the K-Mach cut. Maybe it is a useful thing to have a name for that term. Okay, so to simplify this term, the convenient thing to do is to insert a complete set of states. So let me write this term out. So the second term is t dagger p1 mu t. Right, so it just comes from the second term in the top of this blackboard here when I expand out the state. So to simplify this, I'll insert a complete set of states here, and I'll write this complete set as a sum over some states x and an integral over some phase space. So you'll see why in a moment. P twiddle 1, P twiddle 2. Well, this is just some phase space integrals. I will get a factor P1 prime, P2 prime. It's this state here, T dagger, and now I'll insert my complete set. I'm putting a complete set in here, keeping my particles 1 and 2 in the game, right? They're exactly stable particles, so they've got to be in the complete set. And the T dagger doesn't get rid of them. X is some sum over any other thing, right? Now I want to be in a region where my momentum transfer are small compared to masses, so I can't pair create particles. So all this X is going to be are a bunch of graviton states. But there can in principle be a bunch of gravitons in there, you know, 1, 2, I don't know, a bunch of gravitons, right? Now, so then continuing. Oh dear. Good. So now I'll have this commutator here. The P1 momentum operator can hit this state P twiddle 1 and give me some contribution to momentum. And the other side of the commutator will pick out a P1. Otherwise, I'll have a T, P1, P2. So now I need to multiply. Sorry. So when I write these X's here, let's just multiply by. Yeah. So P tilde 1 minus P1 index mu. Okay. Yeah. So this term here, this was an amplitude, P1, P2, 4-point amplitude. This term is more complicated. So it is a product of amplitudes. There could be many other particles in here, right? So it's not necessarily, and this isn't necessarily a 4-point amplitude. This isn't necessarily a 4-point amplitude. But this thing is a cut of a 4-point amplitude, a weighted cut because you have to multiply by this P1 tilde in here. And P1 tilde is the momentum of that particle there. So there's some stuff in the cut that you've got to throw in there. And then you do your phase space integral. Anyway, you can extract the information from this, from a 4-point amplitude, a cut of a 4-point multi-loop amplitude. Good.
Sorry, can I ask a question?
Yeah.
So the two terms, they have different, so the second term has 2t and the first one has 1t. So in perturbation theory, there is a mismatch in coupling, right? In order, sorry.
Well, yeah, perturbatively, lowest order thing is just 1t. It's next to leading order, then you need the one with 2 t's.
Okay, so does it have a meaning like the second term fixes something at the starting from the second order?
Yeah. That's right actually. It probably fixes up a couple of things at second order, next to leading order. But yes, yeah, that's one way of thinking about it.
Thank you.
Yeah. Okay.
When you inserted a complete set of states, you're assuming that there's always two massive particles. So is that like takes into account like the Goldilocks approximation that you're not forming black holes or like things like that?
That's right. Yeah. That's right. Okay. I mean, clearly in a quantum mechanics process, you could have a hard process of pair creation. That's not classical. So here at the classical, this domain of validity, at the classical approximation, my massive particles, I think of them as billiard balls. They're scattering off one another. You don't create billiard balls in a classical scattering process. You definitely don't create black holes. Thanks.
Quick question. So when you resolve the commutator and like act with the P on the left and the right, how do you pick which momentum you pick out of the multiparticle states? Because like it's not clear to me that there's a prescription for which part of the Fock space the P acts on. So you have like the difference of two momenta on both the first and second terms. Why not the other choice of initial or final momenta?
So maybe this is the most confusing one, right? Because so from here, this started out life as the commutator of this P and this T, right? Now it is the momentum operator of the quantum field 1, right? So now the stuff in this state that involves quantum field 1, by hypothesis, there's only one. There's this and there's that. So the X's here are all light, massless particles, gravitons, photons, whatever, stuff like that. I'm not allowed to create new particles of quantum field 1. So that wouldn't be a classical process, and it violates my conditions that the momentum transfer is small, this Q. This momentum is small compared to the masses of the particle.
So sorry, where in the setup is it implicit that it's the P is picking out the momentum of the first particle then? I'm sorry, I'm just a little bit unclear why it's postulated.
It's just when I set it here. So here I put in momentum operator of particle 1.
Okay, thank you.
Yeah. So, I mean, if you did, it's actually very interesting to put in other momentum operators, to be honest. But in this, the theory I have in mind just has my two massive particles, 1 and 2, the quantum fields for those two massive particles, and then gravity. So the total momentum operator is momentum operator of 1, momentum operator of 2, a momentum operator in the gravitational field. And it's really interesting to see what happens when you put the momentum operator, the gravitational field in here. But yeah, that's the only one that's left. Okay, cool. Yeah. Okay. Excellent. So now, what I'm going to do in the rest of this lecture at the moment now is discuss just the lowest order approximation to this impulse. On my laundry list of things for tomorrow is the next leading order approximation to the impulse. But today, let me just talk about the lowest order. Now, at lowest order, that means I get to ignore this second term. Right? I get to ignore this cut term. So I'm just going to talk about this first term, and I'm going to talk about this first term in the lowest order approximation. Okay, so good. So I will therefore be looking at this term, inserting it into this expression here. And I want to make some simplifications to deal with these phase space integrals and get formulae which are a little bit more explicit that we can go ahead and look at. And I'm planning to give you some homework to keep you happy. I'm sure you've got plenty of time for homework. Yeah, maybe next week. Okay, so good. So I'm going to think of the process like this. So I have particle 1 and particle 2 scattering. So particle 1 comes off with the final momentum, which I'm going to call P1 plus Q. And particle 2 is going to come off with the final momentum, which I'm going to call P2 minus Q. Right? So good. So I will simplify. So there's going to be 2 steps in the simplification. So the first thing I'm going to do is, in this phase space integral here, I'm going to integrate over the momentum of particle 2 using the momentum conserving delta function. And the second thing I'll do is I will make a change of variable. The change of variable will be to set P1 prime equal to P1 plus Q. Right. So this P1 prime here, it'll become d phi of P1 plus Q. Right. And I'll think of Q as being the variable of integration. Okay, so now is when I get the lengthy expression. So let me rearrange these blackboards for a moment. Let's see, honestly. Ooh, I do like that one. Awesome. Okay, well, can we see this? Yeah. Okay, so delta P1 at leading order is going to be, so from here, I'm going to get some bunch of integrals. There'll be an integral d phi of P1, P2. So those are the phase space integrals that I haven't touched. I've integrated over P2 prime using the delta function, and I've made a change of variables for P1 prime. But I have to remember that I've got these delta functions here. Right? So there will be a delta function. Sorry. There'll be an integral, first of all, involving d4q. Right? So that's from the change of variables for particle 1. Now these delta functions, so there's two delta functions for particle 1 and particle 2. Their job is to enforce the on-shell conditions for particles P1 prime and P2 prime, like outgoing particles. So that on-shell condition is going to be delta P1 plus Q, delta P1 dot Q plus Q squared, 2P1 dot Q. So I'm just squaring P1 plus Q there, subtracting M squared, because I know that P1 squared is M squared. That's enforced by that d5. There's another delta function for particle 2. It's just got a minus sign because it's P2 minus Q squared. There are theta functions. So those are the theta functions that set the energy positive, these theta functions that are here, so on that delta plus. Okay, now there's other stuff coming from here. There are wave functions, phi star, P1 plus Q, P2 minus Q, so that's P1 prime, P2 prime, phi of P1 and P2. Okay, the translation operators. Well, this one simplifies up a bit already because P1 prime is P1 plus Q. And this is e to the minus I, e dot Q over h bar. Now, so what's left is the sort of first term stuff there. Let me say times. Come down here. No, isn't that much more. So there's a factor I, a Q mu, because P1 prime minus P1 is Q. And then the 4-point amplitude. Let me write it as A40. So that is the 4-point amplitude at tree level. All right, so it's quite a lot of writing, but I haven't yet made it, taken advantage of the simplifications that are present in the classical limit. So well, let's use those now. So the first classical simplification is that the Q is very small compared to the P, right? To both P's, Pi. So in particular, that means that in these delta functions, the Q squared is a very small shift compared to the P dot Q's. So I approximate delta 2 P1 dot Q plus Q squared is approximately delta of 2 P1 dot Q. Right. That's something that you need to be careful about. Right. It'll be fine at tree level. It's sort of generally fine. However, one does need to take care about that. It's something that you need to be particularly careful of at higher loops. So discuss that tomorrow. But for now, we don't need to worry, and this is fine. Similarly, these theta functions are always unity, right? Because that amount of energy is very small compared to that amount of energy. So these thetas are just one. And you don't need to be careful about that. That's just fine. Excellent. The second simplification involves these wave packets here. Now, so a way to think about this is, let's just think about, let's say, phi 1 of P1 plus Q. So that's just the wave packet for particle 1. So I need its conjugate, but let's not worry about that. It's a detail. So this thing is, up to some square root of energy, something like this. This thing looks like e to the minus P1 minus, some classical momentum squared. So it's P1 plus Q minus the classical momentum squared LW squared over H bar squared. So we meet this quantity here, QLW over H bar. Well, you see from the inequality in the bottom of that board at the top that QLW over H bar is very small, right? So I can dump the shift here. That shift is just 0. So this is approximately phi 1 of P, right? This makes intuitive sense, right? Classical physics shouldn't be able to look inside the wave packets. All right, so then delta P1, mu at leading order becomes So there's this integral over P1 and P2. There's an integral over the Q's to P1 dot Q to P2 dot Q. And the thetas are 1, phi of P1 and P2 quantity squared, e to the minus I B dot Q over H bar times A40, IQ mu. Okay, now we have a bit of a notation for this. You see, this wave packet now is just something that's steeply peaked at the classical momentum. So when I do this integral over the phase space of P1 and P2, its job really is just to say, those momenta, you should evaluate them with the classical momentum. So we write this thing as, so there's this double angle brackets that was useful to introduce. It takes care of the phase space integrals. And those wave packets, e to the minus IB dot Q over H bar, IQ mu, A40. So the meaning of this is place PI equal to their classical values at the end, basically, and impose PI dot Q equals 0. You should do that at the end. There's certain classic cancellations which occur at loop orders which you need to take care of before you can actually do that. So that refers to these delta functions. Okay, how long do I have left? Should we break now, or Dave? I want to give the homework, and it's just a question whether I write it up now or whether I write it up during the break, I guess.
Yeah, it's fine. We can go a couple of minutes over.
Okay. Awesome. Okay. So, yeah. Okay. So I do have one quick remark. Well, actually, so if you think of this this tree amplitude as some number over Q squared plus a constant plus a polynomial in Q squared, then it is worth noting that the integral delta 2 P1 dot Q delta 2 P2 dot Q e to the minus I B dot Q over H bar Q mu times these C0s plus C1 Q squared plus dot dot dot. Well, this thing is going to involve, you see, the Q mu I can trade for a derivative with respect to B. So then it's gone. I can integrate out two of the components of the Q using these delta functions so that I just have a two-dimensional integral. And all that's left is, well, times the C0 is just an e to the I B dot Q. Right? That gives you a delta function. The delta function in impact parameter space, delta 2 of B. Right? But this whole setup is designed so that B is large compared to other quantities which I'm not computing. So B is definitely not 0. Right? This delta function only goes off when B is 0. So it's 0. Right? So you get to throw away this term. Contact terms are irrelevant. Well, these kind of contact terms are irrelevant classically. Similarly, these Q squares here, well, they just give you derivatives of delta functions. So they're even more 0. So the only thing you care about is that one. Right? You just care about the pole term. So that's why yesterday I chucked away any contact terms. Okay. Now, yeah, so the homework. Well, the homework is sort of 2 steps. You can compute delta P mu in GR. We worked out the relevant scattering amplitude yesterday. So that's step 1. You'll need to do some bunch of integrals, right? Yeah, they're not so hard. And step 2, compute the delta P mu for 2 black hole scattering in GR from the geodesic equation. Right. You should get the same answer. You'll, in doing that, you'll see why I was so careful about the sign of A4. If you get the sign of A4 wrong, the black holes repel one another instead of attracting. That's bad. Supposed to attract. Gravity is attractive. Okay, it's a good place to break there. So yeah, we can meet again soon.